Okay, I think we'll get started. So today we're going to talk about chemical equilibrium. So we've been coming off of developing this rigorous approach to thermodynamics, and now we want to connect that to a reaction. So we had, up to this point, we had been able to talk about a mixture of different species, but the reaction, the chemical reaction and the stoichiometry associated with that reaction will link all the different species together. And that will then give us our important equations of thermodynamics, the delta G equation, and so we'll see how we derive that. It's be kind of a big mess, and so you might have to carefully go through this sort of step by step on your own because it's a lot of algebra, but it's very straightforward. So let's get into it. So let's take a general reaction, and I know this isn't completely general, but I think it's general enough for you to get to the idea that how it would generalize to any number of reactants and products. So we've got this reaction, and the stoichiometry is written as such: A moles of A plus B moles of B go to C moles of C and D moles of D. It's this stoichiometry that connects the D ends. They're all connected by this chemical reaction. One cannot change without the other changing. And so how they change, so what that means is we can just talk about a single dN. Okay? And let's let A dN equal dNA. And then let's see how that plays itself out. So if we look at the change in B, well, the change in B is going to be given to us by B over A times the change in A, right? But the change in A is A dN as we've defined. So dNB is just going to be, dNB is just going to be B dN, little b dN. And likewise for C and for D. And so we're pulling these stoichiometric factors in explicitly in now to the dN, the dN being not any one particular species, but actually the single connected variable that's given to us by the reaction. Okay, so let's work at constant T and P, so typical laboratory conditions or body conditions. And that's going to suggest to us that we will want to work with delta G. If we were at constant temperature and volume, then we would want to work with delta A, Helmholtz free energy. So we look at dG, and its natural variables are T and P, and we're holding those constants. That's what's so nice about delta G here, is those will go to 0 and leave only the chemistry, only the chemical work terms. And so let's express dG like that, and now let's do it explicitly for the species in our container. And we're assuming here now that we're not having our species just go off out of the system. They're confined in this system, and their chemical reaction is the only way that they change. So this is our dG. Notice the stoichiometric factors are hiding in here. And there's lots of little D's and little A's coming around. We'll just kind of be careful with where they are. That the context should get the meaning of those. So let me factor out the dN. That's going to be common in all terms. And then we leave the stoichiometric factor times the respective chemical potentials. Now, what is equilibrium? So let's look at equilibrium from a chemical potential perspective. I think that's really the most fundamental way to look at equilibrium. The chemical potential is the potential to change the amount of material. So let's simplify this to just A goes to B. Chemical potential A wants to turn it into B. Chemical potential B wants to turn it into A. The reaction will come to equilibrium when the chemical potentials are equal. The analog here is with voltage. So a chemical potential is analogous to an electrical potential. Electrical potential wants to move charge, or a voltage wants to move charge. Chemical potential wants to move material. So if two voltages are equal, then the charge won't move. Okay? But if there's an imbalance in the voltages, then the charge will move. Well, if two chemical potentials are equal, then the material won't move. But if there's an imbalance, it will move. However, it's more complicated because we could have a very complex equilibrium structure, or a reaction structure, with more than just A and B. And that's what we have in this case. But at equilibrium, the condition is that the reactants times their respective factors must be equal, right? And the reason the stoichiometric factors come in there is because the chemical potential has to move A moles of A, and the chemical potential of B have to move B moles of B, and C moles of C and D moles of D, and those have to be equal. So think about this a bit, but this is I know this needs to be rigorous, but this is a physical statement here, right here, not a mathematical statement. The physical idea that at equilibrium, the chemical potentials are equal. So this is our criteria for equilibrium. Well, what does that mean in terms of this? If this is true, then the thing in parentheses here is 0, and that implies dg equals 0 at equilibrium, which is, if you've had a course in thermodynamics, you well know that we often look at dg for our equilibrium criteria if we're at constant temperature and pressure. And we recover that here directly from this equation. Now let's look at two cases where we're out of equilibrium. Either the reactants are stronger than the products, then this will be a negative number. This will be a positive number. This will be positive, but dn will be negative, because we're going to remember dn. Let's look at how it's defined. If dn is positive, then A is increasing. If dn is negative, then A is decreasing. So if this is bigger than this, then this is positive, but this is negative. So overall, this whole thing is negative. And the reaction will want to move this way because this is bigger than this. So the reaction will want to move forward. And you probably remember, this is how we usually learn the condition for spontaneity in the forward direction. It's delta G, or dg, is negative. Conversely, if the products are stronger, want to push back more, then the reaction is going to go the other way. And this will be and delta G will be positive, because this will be positive. And then the way we defined dn again is if dn is positive, then we're making more A, so we're going in that direction. All right, so this is the criteria for going backwards. And so maybe you've learned about Le Chatelier's principle, and if you disturb the equilibrium, it will readjust to reestablish that equilibrium. So you put a disturbance in, this is no longer true, either one of these cases will be true, and that'll tell you the direction of the reaction. Okay, well, let's get into the nitty-gritty of the details here. So we're sort of taking this as one of the things that you should know for this course. So this is the chemical potential. If you've forgotten this, I'll just state it here, that the chemical potential of species I is the chemical potential at some reference plus RT times the activity of species I. So let's look at equilibrium. Our equilibrium condition is this, right? But let's plug in now this for each of our species. So here is mu A. Here's A mu A, right? Here's B mu B. Here's D mu D and C mu C. So that's our equilibrium condition right here. Let's get all of the reference chemical potentials over to one side. And we're going to do so that we have products minus reactants, which is the typical way that we do things in, say, a general chemistry course, for example. And then on the right-hand side, there's going to be a common RT, and I'm going to actually pull out a minus RT. And I think I have this incorrect. Let's go to C. These are the log of the activity terms. And what I've done now is I've used a property of log to bring just this stoichiometric. I'm leaving the RT because it's in every term and we're going to factor that out. But property of logs, A log X equals log XA is what's being used here to get these all up into the exponents. And then we're going to get, so they're going to get RT, ln. Now we're going to use property of logs. These add, so they're products. These subtract, so they're, we can divide by those. And we get this expression. Now, this is equal to K, the equilibrium constant. Equilibrium constant. And this is defined this way. And I'm not quite sure the reason. My guess is the reason is that as we teach chemistry to new scientists, we can't give them everything at once. And so the way the history of how we learn our profession goes is that in general chemistry, we just don't talk about chemical potential. I think that's kind of a shame in my opinion, but we've just decided we're going to wait until a course in physical chemistry to talk about chemical potential. And so we talk only about Gibbs free energy. And so we say that this is delta G. We know, and a really precocious general chemistry student might figure this out, we know this can't be true, strictly speaking, because this is units of energy, and this is energy per mole. And so these can't really work, but how they're understood is that this is really this, or another way we say that is this is associated to the reaction as it's written. So if we were to multiply this reaction by 2, which we certainly could do, right, as long as we multiply every stoichiometric factor by 2, this value would change by a factor of 2. We'd have to multiply this by a factor of 2. So by connecting this to the stoichiometry, then the units problem is carried by the stoichiometric factors. And so that's that subtlety there that is just hidden to those learning general chemistry. It's just not even mentioned, and then you hope that no one asks about it. But this is what's going on there. Okay, so this is one of the most important equations in general chemistry. So when you're in a typical college general chemistry 2 course, this is critical. But we want to get out of equilibrium as well, because we want to be able to understand the reaction through its whole course. So let's get out of equilibrium. So let's just define. So we're going to define the delta mu for the reaction as this, right? Whatever it is, wherever it is in the reaction. So let's plug in then now each of this. So we'll do something very, very similar. We'll just plug all these in. Then we'll collect all of the chemical potentials, reference state. So we're going to get delta reaction chemical potential. This is at the current state of the reaction equals delta reaction at reference, not at equilibrium, reference. And then we have all these log terms. Well, we'll do something very, very similar. We'll pull out an RT, not a negative RT this time, but an RT, and write this so that we have products over reactants again. This whole thing is not K anymore because we don't know where we are in the reaction. This is Q, the reaction quotient. And so then again, by the convention that we decide to call that delta G rather than delta mu, and this delta G reference rather than delta mu reference, we get the delta G equation. So the most important equation in chemical thermodynamics. This is true at constant temperature and pressure. So chemistry done in a beaker, chemistry in our body, chemistry under under many, many situations. Okay, so then this is one of the equations that every general chemistry student should know, and it's the critical equation for chemical equilibrium. And again, this word of caution, this equation can't sit alone. And we can't say this is the equation for this reaction. We have to say this is the equation for this reaction as written directly. So with the particular A, B, C, D. And again, if we were to multiply by 2 or divide by 2, then this and this would have to be divided by 2 or multiplied by 2, and the Q would be either squared or, well, we would multiply by 2 or half here, which would end up squaring that Q if we bring it up. Okay, well, let's pick up one last thing. Let's go back to our definition of G, as we've talked about now, leading up to this lecture. And let's notice this part of that definition. Well, that's just H. Right, so let's just call that H minus TS. And so delta G is DH, and I'm not going to write out DH, I'm just going to leave it as DH, and then TS minus SDT, but we're going to go at constant temperature and pressure, so this is going to go to 0, and so DG is DH minus TDS. And this is always true. Well, true for constant, it's always true for constant pressure and constant temperature. So if we're under those conditions, then it's certainly going to be true for a chemical reaction. And this is the critical equation, the third critical equation that is generally expected to be taught in a first chemistry course. And that is delta reaction G equals delta reaction H minus T delta reaction S. And oftentimes you'll work with the standard state, but if this is always true for a reaction, again, constant temperature and pressure. So certainly if it's true under those more general conditions, then it's true at standard conditions or at the reference conditions. And so if we look up the standard thermodynamic tables, that's what those would be referring to those, and that's the relationship there. All right, so this is chemical equilibrium. Again, maybe try to, I know this is a really messy board, so sit down very carefully. Maybe try a simpler reaction like A moles of A goes to B moles of B, and see if you can convince yourself of how all these stoichiometric factors take place. It's funny how it is easy to get confused, and there's very tempting to divide by B instead of multiply by B. So it's really worthwhile to sit down with a blank sheet of paper and think about it on your own here.